This is Danny Tang. I'm doing the probability stochastic homework 12 problem 2. And problem 2 gives us an input signal which goes through an impulse response HT and the output. And it says that show HT is F conjugate of T naught minus T is the best receiver that maximizes the output signal to noise ratio. And basically what this problem wants us to do is to derive the match filter equation. And so first we define what the input is, and the input is a combination of x of t equals the signal component f of t plus the noise component n of t. And the output, because we model the match filter as a linear time invariant system, we just do a convolution of the input through the h of t. So output is y of t equals f of t convolved with h of t, which is, we designate this as s naught of t, plus noise, the noise component n of t convolved with h of t, which is the n naught of t. So the SNR equation, or the signal to noise ratio equation, which is the signal component of the output, absolute value, and then square it over the noise component of the output, take the absolute value and square it. And so we can break this down into numerator and denominator. So we know that S naught of t is the input signal convolved with h of t. So we can write this as an inverse Fourier transform of the f of omega times h of omega in the frequency domain. And this is the equation written out with the integral. So then we rewrite this with at peak time t sub d. So we just substitute t with t sub d, and we take the absolute value and square it. So this is the expression here. Now for the denominator, which we know is the noise component, we have to assume that noise is Gaussian and has a spectral density of n naught over 2. And so the input noise signal in the frequency domain is S sub n input equals n naught over 2. And so n naught of t, which is n of t convolved with h of t, is equal to the integral of the two components in frequency domain multiplied together. And then we know that the spectral density, using the spectral density equation of the output, we know that this is just the S sub n input in the frequency domain times the absolute value squared of the integral of the h of omega d omega, and we substitute in the S sub n input with n naught over 2. So then we can rewrite the SNR equation with what we just found in the frequency domain. And so we put what we found with S naught of t sub d, all of it absolute value squared over the n naught of t absolute value of squared. So then you get this expression here, and how we simplify this is we use the Cauchy-Schwarz inequality, which says that if you have an integral of f1x times f2x dx, and you take the absolute value and square that, it's less than or equal to the two separate integrals multiplied together, and the absolute value squared goes inside the integral of both functions. And this is only true if and only if the second function f2 of x is a complex conjugate of f1 of x. So keeping this condition in mind, we rewrite the numerator with the Schwarz inequality we just found. So this equation of h omega times f omega absolute value squared is less than or equal to the integral of absolute value squared h omega times integral of absolute value squared of big F omega. So then we rewrite the SNR equation with a Schwarz inequality. So we have to remember that this is less than or equal to. And then we see that we can cancel out on top and bottom the h omega absolute value squared expression. So then we're just left with SNR is less than or equal to 2 over n naught times the integral of absolute value squared of f of omega. So then, since we maximize this, we know that SNR must be equal to the expression 2 over n naught times the integral of f omega absolute value squared. And remember that the if and only if condition, where the second function is the complex conjugate of the first function. So we know that the h omega is equal to the complex conjugate of f omega, and this is if and only if the condition from the if and only if condition of the Schwarz inequality. And then when we write that in the time domain, we get h of t equals complex conjugate of f over the time reversed complex conjugate of f, which is the filter response. So we see that this is true for the match filter because we're using a known input to find an unknown output. So here, so for part A, B, and C, after we find